Vanakkam. Welcome to this video on biomechanics. We have been looking at kinematics, kinematic chains. We gave the example of the upper limb as a serial kinematic chain. Remember, the lower limb can also be considered to be a serial kinematic chain. In fact, we discussed that when the lower limb is constrained by the floor, which is when you are walking. When you are walking, the lower limb is constrained by the floor. So, that is a form of closure, right. It is a closed kinematic chain. There is one constraint at the hip and there is another constraint on the floor. So, any movement of this kinematic chain, which is the thigh shank chain or the upper leg lower leg chain, can happen only between these two constraints. In other words, the hip and the floor constitute the constraints within which the leg can move, right. Likewise, reaching, while we are discussing reaching, of course, we restrict our attention to planar reaching, reaching within a plane. What are the various constraints that are there? Something to keep thinking about. So, in this video, we discuss the kinematics of a two-link planar chain, its forward kinematics and its inverse kinematics. We start our analysis with first principles and we proceed to develop the method for this type of analysis. Right. So, consider the simplest kinematic chain, a two-link planar serial chain. Right. We will also be focusing on 3R or the three-link planar serial chain, which we will do in a future video. For now, we restrict our attention to a 2R planar serial chain, that is of this type. Right. So, there is one link AB, I am going to call this link length as some L1 and another link BP, I am going to call that link length as L2. Right. So, 2R serial kinematic chain. In the case of the 3R chain, there is an AB with length L1, there is a BC with link length L2 and there is a CP with link length L3. Of course, R here refers to rotary joints. These chains consist of only rotary joints. For the purpose of this discussion, you assume that these chains have only rotary joints. So, now a question is, suppose I know the angles that these links make with the horizontal or with the previous link or with the ground, as the case may be, can you find out the end point coordinates? This is the big broad question before us. In other words, suppose I know the joint angle at A and the joint angle at B. Okay, suppose I know that the joint angle at A is some theta 1 and the joint angle at B is some theta 2 with respect to the previous link. Remember this, very critical to remember this. This theta 2 is with respect to the previous link AB, not with respect to the ground. Okay. The question is, given that the link lengths are L1 and L2, can you use principles of trigonometry and geometry to arrive at the coordinates of the point P? This is the broad question. Okay, can you find the location of the end point using joint angles and link lengths? Link lengths are always known, assumed to be known, for example. Okay. This is called as forward kinematics. Let us say I know the link lengths and I know the endpoint coordinate, where P is something that I know. I also know the link lengths L1 and L2. Can you tell me the joint angles theta 1 and theta 2 is the other question. Okay. This is for the simple case of the two link chain. When the number of links increase, this becomes complicated, as we will see in future videos. Okay. Now, if I need to find the joint angles using end point, this is called as inverse kinematics. I know the end point and I want to know the joint angles. it turns out that one is more challenging than the other, we need to perform the analysis and find out which one and why that is the case. Okay. So, let us start our analysis by looking at this 2-link planar kinematic chain, right. The question is, find the endpoint coordinates using link lengths and joint angles. I know this theta 1 and I know this joint angle as theta 2, this is given to you, and the link lengths are given to you as L1 and L2. Can you find out the coordinate of the point P? In other words, can you express x and y as a function of in terms of L1, L2, theta 1, theta 2, some functions of theta 1, theta 2 for example. Can you do that? That is the question. How do we proceed with this analysis? Before we do, let us perform a simpler analysis of this case. Okay. Now, what I am going to do? I am going to take this same link length L1 and the same theta 1. A question is, can I find out the coordinate B in this? The answer is yes, I can find out the coordinate B using theta 1 and L1. How? Well, what is the coordinate of B? It has two coordinates, and an x coordinate and a y coordinate, and that is the x coordinate, is it not? That is the x coordinate, that is the adjacent side of the right triangle ABX for example, or ABX for example. The adjacent side of this right triangle is the x coordinate of the point B. So, I could then express this as, or let us call this as, I am calling these 2 points as x1 and y1. This B is going to have coordinates x1 comma y1. The question is, what is x1? x1 is the adjacent side of the right triangle ABX. Well, I know theta 1. So, cos theta 1 is adjacent side by hypotenuse, adjacent side is AX, and since I know theta 1, I can actually write out x1 as L1 cos theta 1. How am I getting this? Well, because cos theta 1, I am writing in here, cos theta 1 is x1, I have told this is the coordinate, is the adjacent side x1 divided by hypotenuse AB. What is the length of the hypotenuse AB? That is L1. So, in this I know L1 and I know theta 1. So, the only unknown is x1. So, x1 is L1 times cos theta 1. Its y coordinate is this, is it not? That is the opposite side or the side opposite to theta 1. Now, I can write out sin theta 1 as y1 divided by L1, is it not? The opposite side divided by the hypotenuse. Hypotenuse in this case is L1, the opposite side is the coordinate y1, it is the y coordinate of this point B. So, that means I do not know y1, I can write out y1 as L1 sin theta 1, is it not? I am taking L1 to the other side, that means that y1 is L1 sin theta 1. We have not yet solved the problem, it is just the beginning. Okay. Now, but this is not what I am interested in. I am interested, what is the big question? I am interested in finding the x and y coordinate of the point P, not the point B. Point B anybody can find out. A high school student, a 10th standard student can immediately solve this and say, hey, what is the big deal? I am not interested in finding just B. That helps me, finding the coordinates of the point B helps me, but it is not sufficient. I need to find out the coordinate of the point P. Remember, the link BP is at an angle of theta 1 plus theta 2 to the horizontal. How do I know this? Because it is having an angle of theta 2 with respect to the previous link, and the previous link is having an angle of theta 1 with respect to the ground. So, the net inclination of this link with respect to the ground is actually theta 1 plus theta 2. Okay. Now, I can write out, well, actually if I am interested, I can perform a similar analysis. I will leave this as an exercise to you. So, in the right triangle B x2 P, right. In this right triangle, I am interested in finding the location of the point P as a function of the link length L2 and the inclinations theta 1 and theta 2. Remember how I got theta 1 and theta 2, theta 1 plus theta 2. How did I get this? Because theta 2 is the inclination of the link BP with respect to the link AB, but because the link AB is already at an inclination of theta 1 with respect to the ground, the net inclination of the link BP is theta 1 plus theta 2 with respect to the ground. That is how I got this as theta 1 plus theta 2. Perform an analysis similar to what I did with the previous triangle, right. In the previous case I had an x, I could call this as capital X1 for the purpose of generality. So, I am having this x1 and then I am having an x2. Okay. Now, could you find out the location of point P as a function of theta 1 plus theta 2 and L2 in the B frame of reference with respect to the coordinate B? Then I can move this to the coordinate A. So, that is the idea. You could try this as an exercise, you could try this, but I will write out the final answer of this point x comma y as a function of the coordinate system located at A. Can I write this out? The answer is yes. I can write this as x is L1 cos theta 1, which is that, is it not, that, plus L2 cos of theta 1 plus theta 2, similar to the previous analysis, and then I can write out y as L1 sin theta 1 plus L2 sin of theta 1 plus theta 2. Remember, it is not L2 cos theta 2 and it is not L2 sin theta 2, it is L2 cos of theta 1 plus theta 2 and L2 sin of theta 1 plus theta 2, something to keep in mind. This is the required coordinate of the endpoint P, which is a combination of the two link lengths and the two thetas that are involved with respect to the ground. We are interested in computing workspace. What is this workspace? It refers to the set of all points in the plane within to which this point P will be able to reach, right. For example, in a 2 link chain, in a 2R chain, it consists of 2 concentric circles. The region between the 2 circles is the workspace, right. So, I have one concentric circle which is one of these 2 concentric circles, which is the outermost circle. That this is, when will this be true? When AB and BP are parallel to each other, or in other words, the 2 lengths are such that, or the entire chain is elongated completely. There is theta such that theta between AB and BP is 180 degrees, or it is just like this, A, B, P. When that happens, I will inscribe this circle, this big huge circle, that is this circle, right. I will be producing this circle. And when P is such that when it is close to that point, when it is rotated around such that the angle is rather not 180 degrees, but rather 0 degrees, you will have another circle produce this smaller circle. Note that in this white smaller circle, within this white smaller circle, the end effector cannot enter. Why? Because the link length is such that it actually L2 in this case is assumed to be smaller than L1. Because of this reason, I actually cannot go beyond this circumference of this smaller circle, right. So, the set of all points or the area that is shaded in yellow in this case is a set of all points to which this point P or this end effector P can move to. This set of all points to which this end effector P can move to is called as the workspace of this kinematic chain. Okay. Remember, this is a function of the link lengths L1 and L2. The outer circle has a radius of L1 plus L2, the inner circle has a radius of modulus of L1 minus L2. Okay. Of course, if L2 is greater than L1, this inner circle will essentially vanish, but for the purpose of discussion, we must have this more non obvious case. So, with this we come to the end of this video. In the next video, we will be looking at inverse kinematics. Thank you very much for your attention.